section 2, where I take you through the process of how I built a colorblind Twitter account. So who am I? Again, I'm Jake Boyko. It's very easy to find me online. I'm jakeboyko@gmail.com. I'm at Jake Boyko. I'm Jake Boyko at any service that ever existed. And I am red-green colorblind. I actually have like a very severe version of it, where it's not, most people have this like kind of mild color blindness. I don't see color very much at all, but we'll kind of get into a little later, like just how drastic the difference is. For a long time, I worked on Google Docs, but right now I'm kind of unemployed and doing my own thing, where I'm kind of trying to learn new skills and kind of explore some side projects. And this talk is, the output of some of that time that I've spent, so I hope you enjoy it. So before we really get into it, I was not sure how, I'm sure the color, on the projector is absolutely reproduced perfectly, but just in case it's not, and there's any confusion with the pictures, I have the Twitter bot running up right now, and it has all of the pictures in the talk. So if you want to go to @JakeWoodsey or tweet at it with an image in the tweet, it'll send back the colorblind version of your image. The problem is that I haven't load tested it, so it's probably going to fall over if everyone does it, but we'll see how that goes. It'll be fun. So the talk is kind of divided into 3 sections. First, I want to kind of talk over what people see when they see color. And once we know that, it'll be really easy to talk about what I see and how it differs from what a normal person sees. Next, I'll kind of talk over, because my color blindness is so severe, it's actually very easy to model it. And, I'll kind of draw some graphs and show what that looks like. And then finally, we'll go over kind of what the results are. So do these 2 pictures look different to you? Yes. They do. They look almost identical to me. So this is kind of funny. These are 2 doors that are at Google, where I used to work. And all of a sudden, one day they were painted, and I didn't realize it. But apparently, the door on the left is red, and the door on the right is green. So there's the before on the left and the after on the right, and that's the same image pattern with all of the images. And you're only supposed to walk through the green door. That was an interesting today I learned for me. So let's get into it. So how do eyes normally work? So all of you who can see color normally, you have these 3 cone cells in your eyes that each detect different parts of the color spectrum. There are the long wavelength ones that detect the colors that I listed here, red, orange, yellow, and green. You have medium wavelength ones that picks up very strongly yellows and greens. And you have these other short wavelength ones that pick up blue and cyan. And basically, your brain takes the 3 responses from these 3 cells and combines it into a color. So like to give an example, if like the long cell is like going off the charts, like I'm getting a really strong reaction, and then the medium and short ones are kind of getting a weak reaction, your brain will take all of that information and say, the color that you're looking at is red, and like that part of your vision will be interpreted as red. So it's also useful to know when working with all of this, we're not really doing work with real colors, we're doing work with the computer's representation of colors. So it's kind of useful to know how do computers represent colors. So it's actually very simple. You may remember from school that there are 3 primary colors, right? And it's not a coincidence that there are 3 primary colors and 3 cone cells in your eyes. The idea between the primary colors is that each one of them targets one of the cone cells in your eyes. So if you manipulate the amount of that particular one in the image, the idea is that it'll cause that cone cell to respond strongly or not. And using that concept, you can reproduce most colors that humans are capable of seeing. You can't actually reproduce all of them, which is interesting. That was something that I learned when I did this. So most of you, you all work with JavaScript. I assume a lot of you work with front-end stuff. You may know that RGB is a very common way to represent colors. Like the red, green, and blue are the primary colors. And if people in the back heard people in the front laugh, it's because I show pictures of the primary colors on the bottom, and they're red, green, and the landmark Miles Davis album, Kind of Blue. So what's different about me? So you guys have 3 cones in your eyes. I actually only have 2 cones in my eyes. I was talking to my friend Sam about this, who's here now yesterday, and he was telling me that it's because I'm actually missing the gene that codes for these long cells. So the ones that respond very strongly to red and also pick up some greens and yellows and oranges, it's just completely missing for me. So when my brain's kind of processing the signals, it's only getting partial information. So I can't really fully differentiate a lot of these colors. So the consequence for this is I don't really see reds very much at all, and I get weaker response for these other colors, which are very common. So to kind of quantify how different my vision is, if you ignore brightness, like bright green, dark green, and green are all the same color, and you just look at wavelengths of light, normal people can differentiate at 150. So in your head, guess, with only 2 cones instead of 3, how many colors I see?
100.
I see 17. Wow. So that's not with regard to brightness, it's just with regard to pure wavelengths of light. So if you've seen it, so to kind of like talk about how different I am from a normal colorblind person, have you seen those videos online where people put on these colorblind glasses and they cry at sunsets because they're suddenly very beautiful and stuff like that? Well, those people have, they have like a partial response to like one of the wavelengths, or to one of the cones. So like they have like 2 really strong cones, and then they have like 1 really weak one. So the other 2 kind of dominate the third one. So what those like in chroma glasses do is they actually, kind of attenuate the signal response that the other 2 cones have, so that you get more balanced response between the 3 cones. Like the consequence of that is that you can suddenly get like this much more balanced color perception, and you can perceive more wavelengths of light than you could before, or you can differentiate more than you could before. Another interesting fact that I found out, so I took this colorblind test on the Chrome website, and it told me something very interesting. I took the test, and it's like, yeah, you're too colorblind for these glasses to work, but as a consolation prize, here's a bunch of information about your colorblindness. And I'm reading through it, and it's mostly stuff that I've read before. But at one point, there was a sentence that read something like, protonopes, which is the type of colorblindness that I have, will even perceive color in the wrong part of the spectrum. For instance, they'll perceive peanut butter as green. And that completely blew my mind, because my entire life I have seen peanut butter as green. This is the colorblind processed version of peanut butter. I don't know what it looks like to you. I haven't actually shown this picture to anyone yet. But this is what I see when I see peanut butter. Apparently it's brown. Who knew? So this slide is a little dense, so I'm going to spend a little bit of time on it. But this kind of goes through. So this kind of goes through what kind of how it's modeled. So instead of using red, green, blue, there's actually this other color space that's very useful for working with coloring. And that basically just means you can change any red, green, blue pixel into something that lands somewhere in this color space. So the cool thing about it is that it separates luminance, the brightness of a color, from the actual color of it. So like luminance is on one axis, and we just completely ignore it. And then color just ends up on this like little graph here. So to kind of show you how colors land on it, you see this like upside down U thing, where the rainbow kind of follows it, like pure colors in the spectrum fall, red, orange, yellow, green, and then all the way on the other side, blue, indigo, and violet. Then if you look inside, you'll see that I've drawn this triangle with R, G, and B with my like childlike scrawl of handwriting that I meticulously, very scientifically, accurately reproduced this diagram. And these are actually the primary, like about where the primaries actually land. That your computer monitor uses. And anything that your computer monitor is capable of reproducing is inside of this triangle. So you see there's a bunch of stuff that your computer monitor can't do, but the drawing is actually a little misleading because green and blue are actually right next to each other on the color spectrum, but you see there's quite a bit of a distance on the curve between them. So there's not really much that's not reproducible by red, green, and blue. So how is this useful? So basically on the bottom is kind of how my program works. It looks, again, like a lot of childlike scrawl, but it's not hard once you kind of know what it represents. So this line right here, so normal people can see everything that's inside of this U, like all of the colors that land inside of here, and all of my color vision lands on this line. Those are the only things that I'm capable of seeing. So you see all of these lines that kind of meet at this one point, and those are basically all of the colors that I can fuse. Like any 2 colors that land on this single line are 2 colors that I see the same. So what I do is I calculate, kind of like what the line is that I'm working with, which is easy because given any color, you basically form a line with this one point where they all meet. And then you can intersect it with this curve, which is just a parabola that tells you what color I actually see. So you can produce an estimate of the actual color that I see just by, calculating this line and intersecting it with this curve, which never changes. And yeah, I mentioned on the slide that the graph is produced scientifically. That's a fact. So when I was reading on this, so I made the first version of the algorithm, and the results seemed kind of weird. Like a lot of colors were like way too bright, like that had reds in them. It was like there was something obviously wrong, but I could, all my code was correct. Like I checked it 1,000 times, like I couldn't figure out what was going on. And finally, I found this paper from 1944, which shed some light on it. So my entire life, I know, right? Mine was different back then. It's still good, right? Right. So apparently, my entire life, I've always perceived red as being like so much darker than greens. And people would, when I was younger, would always be like, "What color is this?" And I was always able to kind of like tell apart like reds from greens because reds were very dark, and you're like, "You're not really colorblind." And like, yeah, I promise you I am. But I was kind of, we were never talking about the same thing. Like when I said reds were dark, people would kind of agree with me, but we wouldn't, they didn't know how dark I saw them. Apparently, a lot of reds I see as like 1/10 their actual brightness, just because I'm completely missing that whole like that whole long wavelength cone receptor for colors. So they had this like little hint, like at the bottom of like 24 pages that I read, they had this like tiny little equation where you can actually model it. So it's in this another color space, XYZ. It's really easy to get that from RGB, and then you can produce the brightness that I see of a color. And at that point, you have enough to go back to red, green, blue. Like I said, that one color space was basically, all of the colors and then all of the brightnesses. And using that 2 bits of information, you can convert back to RGB and get like an actual estimate of what I see. So for all of the after images, that's kind of what I'm producing. So now that we have all that information, it's pretty easy to like write a Twitter bot on it. Did people use this? Is it still up? It is. Okay, cool. So good for it. So basically, so I wrote it in Node.js, which is why I'm here at all. And a lot of the stuff here was actually new to me. Like, I worked at Google for a while, and they take care of authentication and all of that. So it's like stuff I never really like considered. So it was kind of interesting for me for how APIs deal with this type of stuff. So anybody who's used OAuth knows that like basically to run a bot on something like a Twitter account, you need to authenticate as the user. So when the user basically grants the application permission, you get this like nice little token and secret pair. So for any request that you send to the Twitter API, you send the token with it, you sign in with the secret where you kind of like produce a hash of your message with it, and that's enough for Twitter to say like, yeah, like the bot is allowed to use this. And then at any point the user can like revoke the token, and then all of the requests would start failing. So if someone kind of figured out the password for my Twitter bot and got into it, then that would take it down. Twitter also offers these nice persistent streams. So basically they have this like user stream endpoint where you just send, you basically just like hit it, like send a hanging get to this request, and it tells you when there's a tweet. Like you don't have to keep pulling for information. So basically my bot, when it's not doing anything, just sits there and waits for Twitter to tell it that there is information coming in. And whenever it gets like a tweet or one of the other messages, it can then say like, hey, are there image URLs? And then like download them and actually like do the conversion function on them. So my Twitter bot ends up as this nice little pipeline, right? It's basically, mostly around manipulating the Twitter API itself. And because the Twitter API basically does everything for you, like I was kind of pleasantly surprised like how little I had to do here. So next let's go to how I did. So basically it's hard for you to know if it did a good job or not because it's kind of subjective, right? It's like whether I see the before and after the same for you. So I'm going to kind of like walk through a couple of images and tell you kind of like what worked or not. So do these images look different to you?
Yes.
Okay. They look almost identical to me. So I basically ran my program, I wrote a script for it, over every image that I've ever taken, which was a couple thousand. And I calculated something called the root mean squared deviation for it, which is basically just a long way of saying that it penalizes errors like very harshly. Like anytime it finds a difference, it squares it instead of just taking it. So you sum all those squared differences together, and that basically finds images that have like regions that are very drastically different from each other. And this was the one that came up as the most different. It's actually very ironic that it's this image for several reasons, most of which that I painted it myself. I went to a bring your own beer painting class and got very painfully detailed instructions on how to mix the paints and produce a flamingo. So it just shows with any, enough instruction I can accomplish just about anything. So when I was testing it, all of the images look the same before and after to me. So I had to like, constantly ping all of my friends. Constantly ping all of my friends and ask them like, what's different, what's different, what's different. So I was having a conversation with my friend Lindsay about this one, where she, she goes over all the differences. She's like, there's a lot of oranges in the first one and pinks, and then in the second one, everything's kind of this dull gray and yellow. And I was like, happy. I was like, thanks. Like, I was happy that they were different. Like, thanks. They look almost identical to me. And she sends me a frowny face and the message, your life is sad. No, it's not. Another image that was very interesting. All right, this is a good one. So I had a conversation. So I had Sarah Gorecki look over my slide deck and kind of like look over images, and I didn't realize this would get such a strong reaction. But she pointed this one out in particular as being interesting to her and said that apparently to everyone, the sushi on the right looks rancid, and she said she would not eat it. But then she asked me an interesting question. She was like, does the sushi on the right look appetizing to you? And the salmon in the middle, actually, it does. It looks tasty to me. But the other two do not look that good to me. Like, I know it's good because my friend Tyler made it for me. He's not trying to poison me. And, you know, I try new foods, so I've eaten a lot of sushi. So I know it's probably good. You know, it doesn't smell or anything like that. So, you know, a lot of the foods I eat, I guess, you know, it made me kind of realize that I, you know, maybe know more of a mental level than like kind of a physical or visceral level that is good. There were also some images where there were differences, where it didn't kind of produce an identical before and after for me, and these were kind of interesting for me. So in this one, does the table on the right look brighter to anyone on the left?
Yeah.
Like, a lot brighter? Yeah. Okay, so this was an image that, again, so I was talking to Sarah about this, and she was pointing it out as not really looking that different before and after. You know, she was maybe saying that I should try to find another image, and that was interesting to me, because I actually view the one on the left as being maybe like 50% darker than the one on the right. Like, that was an image where it really looks like it failed to me. Like, it didn't reproduce quite what I see. So my theory of what's going on is that there's more red on the one on the left, and you know, I systematically perceive reds as being very dark, so it looks more different to me than it does for her. But I was too lazy to actually look up like RGB values for it, so that's just kind of a guess. And this blue arrow kind of pops up in a few places. Like here, the shirt that I'm wearing on the right looks way brighter than the shirt on the left. And another interesting thing here is that in this one, I can actually see a color shift. Like my dad has a shirt on, and I can see that I think it's greener on the right than it is on the left. But I'm not quite sure what the color difference is. I can just kind of see that it shifts. The effects actually appeared much more strongly in this one. This is the 5th most changed image out of any image that I've ever taken. But in this one, I can actually see that the table shifts from red to green. Like for this particular shade of red, I'm guessing it's red.
It is.
I should have asked someone first. Is it red?
Yes.
Thank you. So in this one, I can actually see a difference. So it didn't really do a good job of reproducing it. But then, you know, I was talking to my friend Hannah about this, and she said that like everything about the image looked different, like even down to like her skin color. So I think it does like a mostly good job of capturing what I see, but like it actually fails like on like a large part of it. So that takes us kind of to the end of the talk. So I'm just going to kind of briefly summarize what I went over, because I know that there was a lot of information there. So all of you guys see color with 3 codes. I only see color with 2 codes. This means that I see about, you know, roughly speaking, like 1/10 the number of light wavelengths that you see. Because my color vision is so severely bad, it's actually very easy to graph that one graph that looked like it was an upside down U. And using that, you can calculate these confusion lines of things that I see the same to actually find an estimate of the color that I see. I wrote a Twitter bot in Node.js that works on this. You know, I'm going to keep it up if you guys want to send images to it in the future or show your friends, like feel free. And the images look pretty much the same to me before and after, so it did a pretty good job. And that's everything. So does anyone have any questions? Over here.
To the best of your knowledge, is there a degree of variation between the colors that people see who don't have any type of color blind?
So the question is there a variation between people who have normal color vision? And the answer is yes. This paper from 1944 had a lot of information on this, actually, and they said that based on things like the color of your lens, the color of your aqueous humor, which is like the gel in your eye pigmentation and stuff like that, there will actually be quite a lot of individual variation within groups. But it's not as strong as the difference between the different types of color blindness and the difference between color blindness and normal vision. Yes?
Do you have your phone on you right now? Could you take a picture of the crowd and
oh, sure.
Bot? I'd love to see what we look like.
One, two, three. All right, I'll tweet that out a little later. Over here.
So what did you use in Node.js to change the colors of the images?
I wrote my own code to do this. So I did not, for the life of me, want to actually do image encoding and decoding because that's horrible. So I used a library called lightweight image processing that some gentle citizen of the internet put on. So by the way, this is all on GitHub. If any of you are curious about how the code is written, I'll send this slide deck out somehow, and there's a link at the beginning where you can look at it. All the way back.
Do you ever have issues with like advertisements who think they've done well contrasting colors, who haven't, and they just get merged together?
So the question is, do I have trouble with advertisements? And the answer is, I have a lot of troubles with advertisements, but usually color isn't one of them. Every now and then something will look weird to me, like the new Late Night with Stephen Colbert sign actually looks a little strange to me because it's red on blue, but it's like a dark blue, and the red looks dark red to me. So the sign kind of looks muddled in general. Over here.
As a front-end developer, what can I do? What kinds of palettes do I have to make sure that you're able to get to my site?
So the question is, what type of palettes should developers use? And the answer is that I have trouble actually answering that because I'm colorblind.
Has your algorithm identified any that are better than others?
Should we go back to the correct color from the 60s?
Having been on some of the trains in New York City, you should not go back to the 60s.
Does ARIA define any color palettes that would help in this case?
I'm not sure. I know I've spent a lot of time with the color picker that Adobe has, and that generally does a very good job of bringing up differentiable colors. So if it gives you something very similar to what you're using, then that's honestly probably fine.
Okay.
Over here.
Do you have a favorite color?
Do I have a favorite color? I wore a lot of black in high school. Way in the back.
What color was the dress?
I actually tweeted that. So it was always, I could never see white and gold. It was always blue and black to me.
Yes!
Epilogue, I color processed that picture and showed it to all of my friends. And friends who could see one or the other could see white and gold in my picture. So it was a problem of my end. Over here.
There's this guy on the internet, Neil Harbison. He has this antenna that helps him see color because he's also colorblind.
Okay.
And the antenna sort of brings an object up to the antenna and tells them sort of what color it is. He feels it. Right?
Yeah.
Have you heard of this, or
no, I haven't.
Any sort of implants along these lines?
So the question is, have I considered implants? Okay, so
something so you might feel it.
Right. So have I found useful tools for either knowing or feeling what color something is? And I've tried some apps on my phone to do this. Like when I'm clothes shopping, if I'm not sure if something's blue or purple, I'll always put my phone up to it. But it always gives me these unhelpful labels. It'll be like, this color is shooter or T, Earl T or something. It's never rooted in an actual color name, so I never know what I'm buying. Yes.
Did you ever think of making like a browser extension that just changes the color palettes to something you can see, kind of going off of that question?
Have I considered building a browser extension to better differentiate colors? I have considered that. It's a harder problem. You need to know kind of how to spread the colors out. But I know a lot about it, so I can probably figure it out, but I haven't yet.
It'd be cool if you make us browse the web.
Here, there's a lot of questions. If you have more, feel free to find me after the talk. I'll stay as long as people want to talk to me. Thank you.